All right, can everybody hear me? Okay, I'm Jay Boisseau, and I'm the director of the Texas Advanced Computing Center. I'm going to give you a relatively quick update on the Ranger system and project at my center, and I'll invite you to, if there's time, I guess you can ask a couple of questions. Hopefully I can answer them. It's a big team working on the project, and as we got closer and closer to supercomputing, the number of people that were required to stay in Austin to keep working on the project kept increasing, so now I'm the only one from the project here at SC, and all the rest are actually probably working on Ranger as we speak right now. A little background, the case for more powerful computational science capabilities has been made many, many times over the last few years. The Rising Above the Gathering Storm report, the cover is there on the left, it's sometimes abbreviated the RAGS report, is a widely read report now. It deals with the importance of computational science for knowledge discovery, but also for economic productivity and competitiveness. In other words, how important high-performance computing is to society as well as science. You can see this middle cover is specifically about American competitiveness and the importance of high-end computing in American economic competitiveness. This last cover here is the National Science Foundation Investing in America's Future. It's the NSF Strategic Plan. So we're seeing lots and lots of increased attention to the importance of advanced computing technologies and expertise and the required training to develop those technologies and implement that expertise. The document that perhaps most drove this project is listed on this page, and that's the Cyber Infrastructure Vision for 21st Century Discovery. It's the NSF Cyber Infrastructure Strategic Plan. This plan was released in March 2007, and it articulates the importance of cyber infrastructure overall, and then has chapters on various aspects of cyber infrastructure, on computing, on data and data analysis and data management, on collaborations and networking in communities, and on workforce development. So therefore, you can really think of all of the recent NSF proposals related to high-performance computing as being related to this overall cyber infrastructure strategic plan. And there's certainly other proposals and solicitations and programs that are related to this program as well, because it's really a cyber infrastructure vision, not just a high-performance computing vision, but that is a fundamental piece of it. And we're seeing the first programs in high-performance computing under this umbrella come out now. The system that we're talking about today is the first of the annual NSF Track 2 systems. There's also a Track 1 system, and there are various complementary solicitations. One of the myths about this program, people hear about this award and they're like, oh, great, NSF spending all their money on hardware. Well, not even close. So this award is only half for the acquisition of the system. The other half is for supporting it and supporting the national science community and using it. In addition, there are other programs specifically targeted for getting people to develop software that enhances this system, for developing applications that most effectively utilize this system, and for developing new education, outreach, and training programs that train the next generation of computational scientists to develop and use such systems. So this is the first of these NSF Track 2 systems, and it's 1/2 petaflop. TAC was selected for the first of these systems. It's a $30 million acquisition. I seriously doubt that you could go to Sun's website and buy this system for $30 million, but that was the nature of the one-time partnership for this particular solicitation. It's a Sun constellation cluster, AMD Opteron processors, expandable configuration. I apologize if I say things. It sounds like the project has been talked about over the weekend before now, so I may be redundant here because of my timing in the program, and I apologize for that if I am. The project includes 4 years of operations and support. That's everything from system maintenance to user support, also to technology insertion, and there's a $29 million budget there. And that budget is actually distributed across a number of institutions. When you're deploying a world-class computing system, the likes of which really the world has not seen, then you can't possibly expect that no matter how proud you are of your organization, and I'm sure no director is more proud of his center than I am, you can't really expect that you have all of the expertise required to solve problems that no one's ever solved before. So we have a team of institutions. TAC is the lead center in this proposal, but the Institute for Computational Engineering and Sciences at the University of Texas at Austin, which is a world-class interdisciplinary applications research institute, is also playing several major roles in this. That slide's actually out of date. It's actually called the Cornell Center for Advanced Computing now. So they've recently reorganized, done some different things, and so the Cornell Theory Center, the name you may have known it by since 1985, is now the Cornell Center for Advanced Computing. And the Arizona State High Performance Computing Institute are also playing some roles in here. I'm the project director. Tommy Minyard is the project manager. We have 3 co-chief application scientists, 1 each from Sun, from TAC, and from ISIS at UT Austin. And Jim Brown in the computer science department and also in ISIS at the University of Texas is the chief technologist. The system summary looks like this. I'm just curious, has this already been presented this weekend? Oh, good. Okay. Well, this is the high-level overview of the capabilities and sort of a summary of the configuration. It's not a very detailed configuration. The compute power is 504 teraflops provided by 3,936 Sun 4-socket blades. That means 15,744 AMD Opteron Barcelona processors. And I didn't put the other number, but it must be 62,900 and something processing cores. The memory is 125 terabytes. We actually put substantial memory in here. We probably could have gotten away with 1 gigabyte per core for lots of the applications in our space. But we recognized, since we were competing for the very first Track 2 system, that was going to be a step function over and above all current NSF systems, that there were certain things that we wanted to do. We didn't want to do a specialty system. We didn't want to do a Blue Gene, for example. We didn't want to do a non-Linux OS, for example. We really wanted it to be x86-based, to be Linux-based, and to have enough memory for the full suite of NSF applications. Now, we don't pretend even Ranger is optimal for every single NSF application, but the point is that it's probably well, not probably, we believe it's definitely the best solution for the largest number. Whoops, I need to put my phone on vibrate here, don't I? How about that? The best solution for the largest number of NSF applications. Likewise, we configured it with lots of disks to make sure that we could handle some of the data-intensive applications. So you can see that it's got 72 thumpers in it. There'll be 1 petabyte in the largest work file system, but 1.7 petabytes of disk overall managed by Lustre. The interconnect is an InfiniBand-based network. I'm sure that there have been details here on the Magnum switch up to before me. So we actually have 2 of these switches, 3,456 ports each, full non-blocking 7-stage close fabric with the Mellanox Connect XIB cards. This is a bit more detail on the management nodes. There are 4 login nodes, a ROC master node, 2 SGE servers, 2 N1SM servers, 2 subnet managers, 6 Lustre metadata servers, 4 archive data movers, and 4 external grid FTP servers. So just the management infrastructure for this system is comparable to the first cluster probably that we deployed about 6 years ago. The Ethernet networking capability is 10 gigabit per second capability to wide area networks, 2 in particular, the TeraGrid network and the National Lambda Rail network. This is the Ranger IO subsystem. Probably you've talked about thumpers and things more in this meeting, so I'm going to move over this and we can come back to it if we need to. Talk a little bit about Ranger space, power, and cooling. The total power is about nearly 3.5 megawatts, nearly 2.5 megawatts required for the system, and another megawatt for cooling. We're using a really interesting APC enclosed hot aisle cooling system that's, I have to confess, I was really worried about this. We had to do it. The raised floor cooling capacity of our machine room would not have been anywhere near sufficient to handle this heat density. It's about 28 kilowatts per rack. So in fact, the traditional raised floor cooling system is really only providing supplemental cooling for this system. It's providing all of the dehumidification, but only supplemental cooling. It's these in-row coolers and the hot aisle containment making those in-row coolers more efficient that's really doing the vast amount of the cooling for the overall system. And I'll show you a picture of that coming. I was really worried about how this would look. I knew the racks would look good, the sun racks, but I was worried about how the cooling system would look. I'm going to show you a picture of it, and it looks far, far better than we imagined. In fact, it looks fantastic. APC really did a first-rate job on this. Just a few observations here. Space is really less an issue than power. I keep hearing people talk about the space of their machine room and how much floor space they need, and I just tend to smirk at it because the total space for Ranger is about 4,500 square feet. So we used to also think we needed a 20,000 square foot machine room or 30,000 square foot machine room or more. Turns out what's likely to be the world's most powerful supercomputer requires 4,500 square feet. Now, it requires 4,500 square feet because of the in-row cooling system. It would only be about 3,000 if it weren't for that. And then it requires an extra utility building for the power and cooling infrastructure. So it's really your power and cooling infrastructure are by far the dominant infrastructure limitation. And this is really best articulated if you look at the NSF proposals. For 20 years, power was buried in the indirect costs that your institution charged. Now, power is not an indirect cost. It is a line item that's part of the budget. The power for your laptops and your staff who are doing the work on the system, that's still an indirect cost, but the power for these large-scale supercomputers has been pulled out because they recognize it's a much larger percentage of the project operating cost than it ever was. And in fact, for the Track 1 system that'll come online in 2011 that NSF funded, the power budget for that is not only significant enough to be pulled out of indirect costs, it's likely to be twice the staffing budget per year, which is absolutely unheard of. It's a little bit more on the power and cooling on that slide, but let's jump to the layout here. This is how the system is laid out. The two big S's in the middle are the switches. On the edges of the system, you see the management nodes, and storage systems are in those management nodes. You can see all the C's are the actual compute racks, and the lines in between them are the APC cooling racks. And so in the data center, it looks something like this. This wall right here is the east wall of the data center, and that can be knocked out and pushed in this direction farther than we could ever need. So in fact, while Ranger and the associated PDUs occupy most of the data center, we still have plenty of space for auxiliary systems, IT systems, grid servers, networking equipment, et cetera. We also operate a second machine room that our current high-end production system Lone Star is in. So that's another 4,500 square foot machine room. But the plans are to knock out this east wall, which has actually been designed with the system far enough from it and with no pipes in it, such that we can expand the machine room in this direction and then with a very short downtime take out the wall in between. This is a picture of some of the external infrastructure. This is the stuff that doesn't get factored in when you show pictures like this and talk about the numbers in here, which is the extra utility building outside of the machine room that had to be constructed to manage the power and cooling. The project cost, as I said, it was a $59 million project. That's the full system. It's system maintenance. It's 4 years of operation support. It's also an advanced year of prep work for it. UT Austin is providing power on top of that. So for this very first Track 2 system, NSF Power shared or cost shared the power budget itself, which will probably be about $1 million a year. UT Austin also upgraded the data center infrastructure, which it was $10 to $15 million, but it was a university physical plant calculation, so that's all I'll say on that. TAC upgrading the storage archival system, another $1 million there. So really, depending on how you count all of these other non-NSF expenses, you could argue it's a $75 to $80 million project. If you think about that not over the 5+ year project life cycle, but the 4-year life cycle of the system actually running science, that comes out to over $50,000 a day. So we really have to enable users to conduct world-class science every possible day. And the award has some pretty strict requirements, 95% uptime and 95% of jobs submitted complete. So the NSF recognized that with this size investment in science infrastructure comes a responsibility to use those tax dollars wisely. We have a technology insertion plan. The basic gist of this slide is just that we recognize that if it's a system that's this size and this scale, The software environment will not be mature and robust and maximally effective on day one. People haven't had a chance to even build programming tools to use systems at this scale. So the software environment for this system is going to change dramatically over its 4-year life cycle. That has not been true of all of the systems we've deployed in production. Yeah, we upgrade to the next version of the compiler or the next version of the MPI library, but we expect that these Track 2 systems will stimulate much greater advances in programming tools and system software than we've seen over the last few years. So we actually have a process to build a communications network, to track software that's in development out there, and to provide, say, a few thousand cores at a time for researchers who have software that may be useful on Ranger and help augment users of the system. We don't have a lot of applications performance notes yet. The system has not been completed yet. We have done some projections. So I can talk to you about those offline. The thing, obviously, it looks very promising. We had to include those projections into our proposal. We actually went conservative and were told that our projections looked really good. Our initial assessments of the very first applications are meeting our projections as well. So we expect some applications, a small set will sustain 50 to 100 teraflops of performance, and very large problem sizes may use up to 100 terabytes of memory. So it's really a staggering capability system as well as a tremendous capacity system. The user environment is going to be very similar to Lone Star, a full Linux OS on the nodes. 2.6.18 is the starting working kernel. Lustre file system with a home and 2 work file systems will be available, the largest of which will be a petabyte. Standard third-party packages, InfiniBand using next generation open fabrics, and VAPitch and OpenMPI. We'll actually have 3 MPI libraries and 4 compilers on here. So we have a nice 12-entry matrix for compilers and compiled MPI libraries. And over time, we'll select what are the preferred compiler and MPI library combination. But we really can't do that at the beginning because each of the MPI libraries has some quirks as well as some advantages in terms of scalability and performance. And so it's really important that we offer all 3 of those MPI libraries and 4 compiler options up front while we're still determining which is the overall best compiler for these new quad-core Opterons with dual pipelines. Here's a bit more on some of the user environments, the suite of compilers, the batch system. It'll be very similar to Lone Star, except of course we're using Sun Grid Engine in this project. And some of the baseline math libraries are listed here. And the system configuration looks like this. I mentioned we have 2 work file systems. One is a petabyte and one is about half a petabyte of disk. We're going to have a couple of terabytes devoted to TeraGrid community software, a couple of terabytes for home, actually about 6 terabytes for home directories. There's some user support challenges with a system like this because no systems like this exist yet. There is the large Blue Gene system at Lawrence Livermore National Laboratory, but it is a different system than this. This is a more general purpose system with much more memory and more compute capability as well. We're going to be the first general purpose system at a half petaflop, the first one with this many quad cores, this kind of massive memory and disk. So there are going to be some new challenges on code optimization for quad core, 16-way nodes, extreme scalability to 10,000 plus processing cores, petascale data analysis, and tolerating faults while ensuring job completion. So we recognize it's not business as usual for our user services efforts. It's going to be dramatically different in some ways and harder than it's been the last several years. So therefore, the user support plans do include all the usual kinds of things, documentation, consulting, training, plus there'll be a user committee dedicated to this system comprising active, experienced, high-end users, not the principal investigators in charge of the projects that are using the system, but the high-end, day-to-day users who are really the cutting-edge ones. There'll be a significant applications engineering effort. Some of the FTEs funded by the project will dedicate a quarter or half of their time for months at a time to embed themselves in applications projects and help insert expertise and technology into those projects and teams so that they can get maximum use out of Ranger as fast as possible. We'll develop applications collaborations with the large applications teams around the country, not all of whom will be able to embed an applications engineer in at any one time, but we can certainly provide some directed communications to all of them to help them ramp up quickly. There'll be a very strong support of professionally optimized software. It's getting harder and harder to extract a high level of efficiency out of these very hierarchical systems. So we want to make sure that we support software that has been professionally optimized, that's received significant software engineering effort to be optimal for systems with quad-core processors and many core nodes and scale to high processor accounts. There'll also be additional training, and in fact, one of the advantages of bringing Cornell back into this, the NSF program is they had these things called virtual workshops that years ago were very popular, and we're bringing back the virtual workshops so that people can do asynchronous online training to learn how to use Ranger, as well as we're going to provide more training. So in fact, in the first quarter of next year, we'll provide in-person training for Ranger, not only at TAC, but also in New York City and in Phoenix as well. The impact in the TeraGrid is going to be tremendous. 472 million CPU hours added, which is more than the sum of all current TeraGrid systems combined. Half a petaflop performance is over 5 times the performance of the current peak system. It really will enable unprecedented research and jumpstart progress to Petascale for the entire U.S. academic research community. And it reestablishes NSF as a leader in high-performance computing. NSF established itself as a leader in high-performance computing in 1985 when it created the high-end academic supercomputing centers in the U.S. Created 5 initially. It shut down 1 in 1990, but 4 of them operated for a very long time. Of course, over the last several years in the United States, Department of Energy and Department of Defense have really grabbed the mantle for high-end, in particular the ASCII program. This puts NSF right back up there at pretty much at the adults table for very high-end supercomputing. This is a system monitor that runs on the TeraGrid user portal that shows you the current TeraGrid systems. So you can see how many there are, and really none of them even break 100 teraflops. So in a sense, maybe this is a better graph because it shows it to you graphically. The impact of this system will be to a very large perturbation, adding a tremendously larger HPC system for the national community to use. So what's the current status? Well, let me give it to you in terms of the good, the bad, and the ugly. At this point, it's mostly good. And this is because many of the bad or ugly things have been addressed through tireless efforts by TAC staff and Sun staff. The Opteron quad-core performance is very good. The Sun Constellation Blade performance is good, very good. The Magnum and ConnectX performance, very good. The Sun Thumper performance, we actually had a chance to play with that much earlier on. That's very good. The engineering in the blades and the Sun racks and Sun hardware has been exceptional. The HPC in-row cooling and hot aisle containment facility is working extremely well, and as I mentioned, it doesn't look crappy like we were afraid of. In fact, it looks great. And SGE is actually performing very well. The advanced reservation capability that we needed as part of the proposal has been added. The overhead of launching jobs with it is very low. There is a little bad. There are persistent BIOS issues. Need to upgrade BIOSes for the chips and the blades. In fact, I think we're awaiting a BIOS upgrade for both the processors and the blades right now. There was as to be expected, there was some initial component fallout. I think we're mostly through this right now, but it's always going to be a problem, some fallout due to the massive number of components. There's really not any more ugly, I believe, because I believe that we have this next problem licked. The truly ugly thing that happened was cable manufacturing, testing, and delivery. I really can't sugarcoat it any other way than to say it was an ugly mess for a while. The first cables that we got had obvious crimps in the end of them. The cables are Leone cables, which Andy Bechtolsheim once gave us a half-hour or more sermon on cables, which was really about 29 minutes more about cables than I ever hoped to know. But Andy knows a whole lot about cables, and these are the best cables in the world, these Leone cables. The Molex adapters are the best adapters in the world, but in attaching the adapters to the cables in Guadalajara, well, I don't know what the manufacturing process was that was used, but it was obviously defective when you first looked at the cables because there was a crimp at the end of the cables. Oops, where's that slide? Dang it. I had a slide. Hold on. I want to show you this if I have it. I inserted it the other day. Here it is. It's out of place. Here we go. Well, as I said, Andy knows infinitely more about cables than me, but I probably could have looked at that and said, oh, that doesn't look very good. So we are behind on deploying the large-scale system because the long cables really were the long pole in the tent. We had developed a plan in which we cable all the long cables first because we're really at the limit of even what the long cables that are 15-meter InfiniBand cables, and therefore they're active cables. They need some boost. We're even at the limit of those, so we wanted to make sure and get those in place first and not find out that if we wired all the short cables first, we'd used up some valuable length real estate, and now we're going to have problems making the 15-meter cables fit. Unfortunately, the 15-meter cables and the 13s and the 11s are where the problems were. So that's why the system is not all wired yet. But all racks and power in place, and here, as I keep raving about this, I think really good-looking APC hot aisle containment facility. They even added spacers on top of their racks to match the height of the sun racks so that everything looks nice and flush. They're really nice doors on the ends of the racks as well. It's really interesting to open one of those doors when it's been closed for a while and feel that rush of heat come out at you, but it really does look good and it works well. The blade consistency has also been very good. You can see that on this thing, with the performance of these, you need to look at the bottom axis here, but the performance of the blades has really been within about 1%. So some highlights so far on this page. You can see some HPL and stream numbers here for the processor and the blade. The point-to-point latency has been extremely good. Even across Magnum, it's only 2.3 microseconds. And point-to-point within a chassis, 1.65. The Sun thumpers, we're getting 930 megabytes per second to each thumper using dual HCAs, which is a new feature. SGE, very low overhead per rack, and the advanced reservation functionality is implemented and seems to be working. The system, we do not have a top 500 number for the current list. We've only run top 500 up to about 900 nodes because of the cabling issues. We were able to get a 900 node run to work with the limited number of cables that out of the first batch that were made well enough. And even on that, we exceeded the performance of our current production cluster that's one of the most powerful in the world. So even with a quarter or 20% of the system here, we're doing quite well. Timeline, basically allocations begin in January, so most of this timeline is moot now. Getting access to Ranger, basically go to www.terragrid.org, or even better, go to portal.terragrid.org and click on the Allocations tab on portal.terragrid.org, and the instructions are there on how to get access to Ranger. I'm running out of time, so all I'll say real quickly is there are going to be a few more Track 2 systems. In fact, the second one's already been awarded to the University of Tennessee and Oak Ridge National Lab. We were actually a partner in that one as well. There are going to be a number of STCI and STCI and Peta Apps and CI Team and CDI awards to complete the ecosystem of applications development and software development and training. There's certainly some Peta challenges. You guys have talked about these, I'm sure, in the meeting before this, and I've alluded to them. Linda did a nice job talking about some of the Petascale data analysis challenge. This is going to be tremendous for us. So everybody sees it coming. Unfortunately, we're the ones who are actually going to get hit by it first. The biggest problem we have is that if everything works perfectly on Ranger, if codes scale, the system is reliable, etc., then we have this problem looming, which is generating vast amounts of data that are going to be challenging to analyze. We've talked to Sun about this, and they've sort of implied that they can maybe provide a handful of visualization nodes in there of the type that Linda's looking at, and then we'll probably go write a proposal to go get a whole bunch more once we have some real data on some of these. In addition, Kelly Gates, on our staff, submitted an STCI grant, Strategic Technologies for Cyber Infrastructure, and it was recently awarded funding to develop some software technologies for using Ranger to do visualization within the computations as well. The power challenge I've already alluded to. So in summary, this push to Petascale is driving HPC vendors like the push to 1 gigahertz drove AMD and Intel years ago. It's really exciting to see this. This is the sort of bridge to Petascale system. It's arguably a Petascale system with a half petaflop of performance and over a petabyte of disk In 2008, we'll start to see some peak petaflops of a petaflop plus peak systems. NSF is determined to be a leader in petascale computing as a component of world-class CI, and we're happy to help them do that. Ranger is progressing. It has had some delays. I need to be honest. It's actually had a lot of delays throughout the project timeline. Fortunately, most of them have not been in critical path elements at that given time. And so that's kept us from falling too far off schedule. Unfortunately, it has really resulted in lots and lots of hard work by some really talented folks. We've had some great Sun folks on staff at TAC for the last few months. Our folks have been working very hard on it, and so largely people have overcome the various delays in the project so far. And we still expect to get our first users on in December, which will be tremendous. And so finally, Ranger and these other petascale systems will enable unprecedented high-resolution, high-fidelity, multi-scale, multi-physics applications. And we're excited to be on the cutting edge of that. And so I think that we'll have lots of interesting stuff to tell you in 2008 as the science results come out and we spend less time telling you about configurations and more time telling you about science. So thank you very much.